Welcome to KETIV Virtual Academy. We're so excited that you're here. And thanks for joining. Today's session is hosted by Snigdha Sarkar. This session was actually suggested by one of you during her session last month. So thanks for giving us feedback, guys. We love creating content that's going to benefit you and your company. I wanted to send the link to our KVA webpage so that you can check out our upcoming sessions. And you can stay in the know. If you're watching us on YouTube, please check out that link because we are having some changes coming soon and we want to make sure that everybody stays in the know and everyone has access to the content. If you have any feedback, let us know after the session. The link to give us feedback will show up in your browser. Let us know what you liked about the session and let us know what other topics you would like to see covered. We're really flexible and we love, again, creating content that's going to benefit you. So thanks for joining, everybody. I will let Snigdha take it away.
Thank you so much, Christina. Hi, everyone. Good morning. My name is Snigdha Sarkar. I'm Simulation Practice Lead here at KETIV. Today we're going to be talking about natural convection simulations in Ansys Discovery. Like Christina mentioned, this was requested by an audience member last time. And I thought it was a great idea to follow up a forced convection demo with a natural convection demo. So this is going to be shorter in duration compared to the last one because I covered a lot of functionalities in that particular KVA. Do check it out if you want to see the different thermal capabilities of Ansys Discovery. So starting with the agenda of today's session, we'll talk about how natural convection differs from forced convection and certain considerations that you would keep in mind while simulating a problem like this. We'll briefly touch upon Ansys Discovery capabilities for those of you who are joining us for the first time or maybe haven't watched a Discovery KVA from KETIV. We've done a bunch of different KVAs for Ansys Discovery, so if you're curious about its capabilities, do check them out. And then we'll dive right into the demo. If you have any questions, feel free to leave it in the Q&A box and I'll get to them towards the end of our session today. All right, so natural convection. Convection, as we know, is a major mode of heat transfer. For forced convection problems, it's easy to visualize that there's an external forcing condition or a momentum source that allows fluid to move from one point to another. As it has some velocity, it transfers the heat between those two locations as well. And that would usually be classified as a forced convection problem. But convection can also occur in cases wherein there are no external momentum sources or there's no external forcing of fluid. And this type of convection usually manifests in the form of convection currents, wherein fluid is naturally displaced from a heated region because of density gradients. So you can think of a heat source, say, for example, in the schematic over here, where the fluid closest to the heat source gets heated. The density varies, it becomes lighter, rises at the top, and then colder air rushes in to sort of replace it. So this type of a current is what natural convection usually refers to. And this is buoyancy-driven flow because there's a buoyancy force that's acting on the fluid with density gradients. So as we go through the demo, I'll talk about what are the important considerations to keep in mind when simulating a buoyancy-driven flow. Natural convection is a very common phenomena. You see snapshots here in the slide for a cooling tower or even just, an ocean body and the land adjacent to it, wherein convection currents occur naturally. For today's demo, we're going to look at another electronic device wherein we have a heat source, and we're basically going to see the plume rising from that heat source because of natural convection. So even if you're not doing a strictly natural convection problem, and it's more of a mixed convection problem where both forced convection and natural convection effects have to be taken into consideration, it's good to know what are the underlying physics that you need to keep in mind. For today's demo, like I said, we're going to be doing natural convection, but with the help of Ansys Discovery. For those of you who are new to this tool, it is a unique, one-of-a-kind simulation-driven design tool that allows you to combine instant physics, high-fidelity simulation, and interactive geometry modeling all under the same platform. The best thing about Discovery is that it's not limited to any one particular type of physics. As you can see on the screen, you can do fluid simulations, thermal simulations, structures, electromagnetics, and even topology optimization. So if you're curious about how Discovery can be used for some of these other physics, or if you want to see an example, again, feel free to request it, and we'd be happy to do a future session on those topics. And this is just a screenshot from the last KVA that we did. For those of you who didn't attend it, we did an electronics closer thermal simulation. And in this case, it was forced convection. You can see the fans inside the enclosure that were pushing the air and dissipating heat from the PCB boards. And so we simulated this, but for this particular example, we're going to do more of a natural convection problem when we don't have fans or any external momentum sources. We'll just see the convection current and the plume rising from a heated body inside Ansys Discovery. So with that, let's jump right into the demo. And hopefully everybody can see my Ansys Discovery GUI. If not, Christina, let me know. But I'm using the latest release version, which is 2024 R2. What you see on the screen here is the heatsink and the die at the bottom. So let me go back to the model stage so that I can walk you through the structure tree. So this is the die over here. And then we have the heatsink fins at the top. Now, this geometry is pretty clean, so on its own, I don't have any changes to make to it. What I am going to do, however, is build an enclosure around it, because we have to create a fluid domain wherein we can see that density variation and heat transfer taking place. So let me just go ahead and turn on the Prepare tab. And inside the Prepare tab, you see this option called Building an Enclosure. So you can click on that and just click on the body around which you want to create the enclosure. And what it's going to automatically do is create this box. It doesn't necessarily have to be a box. It could be other shapes as well, as you can see over here. But for our case, a box is fine. And the default cushioning between the object selected and the enclosure around it is 25%. You can go ahead and vary it for different geometries. The cushioning is just the clearance between the body and the extent of the domain you're creating. So what I'm going to do is I'm going to change this bottom clearance to 0 because I want it to match up. And then this top clearance should be big enough for me to be able to visualize the plume. So let's use 80 millimeters and then hit the green check mark over here. And when you hit the green check mark, you can see that this enclosure body was now included in your structured tree. So this is going to be my fluid domain. So other than this, there isn't much that I need to do in the model stage. Again, for those of you who are new to Discovery, the model stage is usually where you clean your geometry up. If it has dirty geometry, overlapping bodies, intersecting bodies, gaps, etc., where fluid can leak out, those are the things that you correct in the model stage. But it's not just about cleaning the geometry. Sometimes you can also prepare your geometry for simulation. Like in this case, we created an enclosure to further simulate this CFD/thermal problem. So once we're done with the model stage, we can go to the Explore stage. The Explore stage is where you can look at instantaneous simulation results. This is because Discovery is using your GPU compute power in the background to run your simulations quickly. Nowadays, in more recent versions, you also have the option to leverage CPUs for running your simulation in the refine mode, which is the highest fidelity mode at the very right in the bar below. But we can stick with the explore stage for our particular problem. It's fairly simple. So before we do anything else, let's look at the physics tree over here, and let's look at the material assignments. So originally, it was just the heat sink body that was supposed to be aluminum. But once we created the enclosure, the entire enclosure gets assigned this material, which is not right because this domain is made out of air. And this die over here at the bottom is made out of silicon, okay? So if you click on any particular material, you can go ahead and change its values if you want to, supply custom values. You also have a table over here if you wanted to, provide temperature-dependent properties. Notice, however, that right now the material panel is only showing me the density. It's not giving me the option to change thermal conductivity or specific heat, which are important properties for a thermal problem. And that's because we haven't told Discovery yet what kind of simulation we are running. Once we choose a thermal simulation assignment, we'll see more properties being populated. So we'll check that in just a second. Let's go ahead and fix the fluid property. So I can click on Enclosure. And on the right over here, you see the material. So I'm going to go ahead and change that from here. By the way, you don't need to specifically choose this from the structure tree. You could also just triple click on a geometry to select the entire volume. And that would also give you the same option. So let's go ahead and choose air. And once you change it to air, the appearance will also change a little bit. You can look at the default appearance properties for each material, and you'll see air in the material assignment panel right now, okay? All right, now having said that, let's go ahead and assign the thermal boundary conditions so that Discovery knows what kind of problem we are solving. I'm gonna go ahead and assign this die over here a value of 20 watts of total volumetric heat and hit enter. And when you do that, Discovery is automatically intelligent enough to populate a lot of the other conditions that are applicable to this problem. So say, for example, we see that gravity has already been turned on. And gravity is an important consideration when you're doing buoyancy-driven flows, because the gravity force is acting on the fluid locally with differing densities. So make sure that this is turned on. You can also go to this settings panel over here. And under physics, you can make sure that buoyancy is included, all right? The other thing is also the gravity direction. So in our case, if you look at the view arc over here, the direction is correct. It's acting in the -z direction. So make sure it aligns with your geometry, however you have oriented it, okay? Now, there are other things in the physics tree that you see. So say, for example, all bonded contacts between the die and the heatsink have been automatically detected. Plus the fluid-solid interfaces, basically faces that are adjacent to both solids and fluids, are again automatically detected by Discovery. And this is where your conjugate heat transfer happens. So these are things or steps that you don't have to perform yourself. So makes the simulation setup that much easier and faster. All right. Now, one thing I would like to point out is we talked about things to consider when doing buoyancy-driven flow or a natural or free convection type flow. We talked about density gradients, but if I look at the air properties over here, you'll see that the density has a constant value, right? And by the way, now you can see all the other properties that were earlier missing when we had not added the thermal type simulation setting to our discovery session. Now you can see all of that over here. Again, if you wanted to vary a value with temperature, you can just populate this table. But going back to the constant density values, if I'm telling Discovery that the air density is constant, then how exactly does it account for the density changes as the flow heats up near the heat source and then rises up? Well, what Discovery does is when you include buoyancy effects, like we just saw in the settings panel, it'll use a Boussinesq expression behind the scenes to account for the local gravity force that's acting on the fluid domain. What that means is instead of working with a varying density, it's using an expression that takes into account the thermal expansivity and the initial fluid temperature to calculate what that local gravity force should be based on that expression. This Boussinesq approximation is not valid for those fluids or those operating conditions wherein you can expect to see a large variation in density because of temperature changes. It is only valid in those cases when the density change in real life with respect to the temperature changes is relatively small. So in those cases, you can apply this Boussinesq approximation, and that will allow your simulation to usually run faster. This is not just unique to Discovery. You also have the capability of using something like a Boussinesq approximation in other CFD tools, especially in Ansys Fluent as well. So that's what it is doing behind the scenes. If anybody was curious about how is it accounting for density gradients, even with a constant density number. By the way, you could also do an ideal gas simulation by clicking on this guy over here. It's going to take longer for us to solve it that way, so let's just stick with the easier method, and this works for most cases. And we can go ahead and complete the rest of the setup. So we've assigned a heat source, we've built an enclosure, we've automatically, gone through the physics list and turned on gravity. The other thing is to define the boundary conditions at the extent of the domain. So typically in forced convection flows, even if you have an inlet with a velocity assignment, you're providing a certain velocity, and depending on the magnitude of the velocity, it could again be a forced convection problem, right? So in this particular case, we are going to assign pressure boundary conditions everywhere. And that way, whatever movement we see in this domain is purely because of density variations or purely because of buoyancy. So let's go ahead and do that. I'm going to go ahead and assign an inlet boundary condition over here. But instead of velocity, let's choose pressure and hit the green check mark. And so this shows up here on the left. And then let's also go ahead and assign a pressure boundary condition for the rest of the phases. We'll name one as inlet and the other ones as outlet, but in any case, it's all zero gauge pressure, meaning open to ambient. Now that we've done all the boundary conditions assignment, including the heat load that we provided at the source, we are good to run our simulation. The only thing that you have to worry about now is, depending on the geometry that you are simulating, you want to make sure that the fidelity of your discovery session is high enough to capture the thickness of the fans, right? You want resolution in those thin fan solid sections. So if you look at the fidelity bar over here, it's on the left side, so the fidelity is quite low. So I would recommend, dragging it all the way to the right for a problem like this. And what that does is it allows you to look at the size preview. And if you hover your mouse over the domain, you can now see what is the fidelity that is being used to resolve your domain everywhere. So if you look here, you can now see that you'll get at least one cell across the thickness of the heatsink in your problem. So look at your geometry, see what is the smallest feature that you need to resolve. If it can be defeatured and not important to your problem, do that. But if it needs to be retained, make sure that your fidelity is high enough to be able to resolve that. Another thing that I covered last time is if, say, for example, your geometry is even smaller than what the fidelity bar can properly resolve, you can go ahead and assign a local fidelity or a local sizing to those faces. We're not going to do that for this particular example because it's going to take a little bit more time to run. But if you wanted to go ahead and do that, you could just box select all these faces and assign it a value less than 0.6 millimeters. All right. So after doing this, we are good to go. There's nothing else to change or assign, and we can directly go ahead and click on the solve button. It takes a little bit of time on my machine, maybe 5 minutes or so for the solution to converge. So instead of making you guys wait, I already have the solved solution over here. You can see all the boundary conditions, etc., are similar to the first session that I was showing you, but this solution is converged. And what you'll notice here, let me change this to temperature, is the plume that we so often see with such natural convection cases. This is what's happening as the heat is being transferred from the heat source to the sink, and then the sink is dissipating it into the domain. And not just temperature, if you look at velocity over here, even though we haven't supplied any velocities at the flow boundaries, you can see that there's movement. And especially if you look at a cut plane, you can see how the flow is moving over here. So you can see a little bit of those convection currents that we early on discussed in the particular problem, right? And you can look at particles as well, depicting the path line of the flow as it moves through the heatsink domain. The important thing to make sure is that you're resolving the space correctly so that when the flow is being computed, it's taking into account these thin clearances and producing the results accordingly. Okay, so I'll wait to see if anybody has any questions. You can also do this problem in the refine mode. So right now we're in the explore stage, but if we go to the refine stage, you should be able to run the simulation with either the Fluent solver in the background if you have a license for Fluent, or you could also just use some additional fluid flow options that are only available in the refine stage. And remember how I said that you can use the GPU or the CPU for running your simulations? So this is where you can come and opt between the two. So if you don't have a good enough GPU on your machine, but you still want to use Discovery, you can keep using your CPU to run the simulation. The only caveat being that in the refine mode, you don't get to see the results instantaneously. It has to run for a couple of iterations And then once you stop the solver, that's when you're able to see the results, just like in most commercial CFD software. And additionally, you could also choose the meshing method. This is a functionality that is missing from the explore stage. So instead of using a tetrahedral mesh, you could also use a polyhedral mesh and get a really high quality mesh that'll give you that much more confidence and reliability over your results. So I would encourage everybody, whoever has Discovery, to try out this problem and maybe solve it both on the explore stage and the refine stage and see if the results are comparable and what are the functionalities you're able to try out in the refine mode compared to the explore mode. So if anybody has any other questions, feel free to leave that in the Q&A box. Otherwise, we can wrap up this session.
Thank you so much, Snigdha. We don't have any questions on the YouTube side. And I just want to remind everyone that you can check out our upcoming sessions following the link in the chat.
Excellent. Thank you, everybody.
Thanks for joining, everybody, and we'll see you guys all next week.
Thank you.